I don't think I said anything funny yet. I don't know what's going on here. Oh, yowzers. Thank you. I got everybody's quiz. Thank you. Thank you, thank you. I have everyone's quiz. All right. So let me just, I'll take a minute of our time to look at the solution to this with you guys. Thank you. If I can find it. Oh, I probably should put the projector on, huh? Let's see here. You can do it. You can do it. It's not listening to me. Oh. Funny thing, if you don't plug the projector into the HDMI port, it doesn't work. Go figure. All right. So, to start with, to calculate the composite of f and g, f composed with g of x, what we do is we plug the formula for g, which in this case is 3x. Oh man, what have I done? Oh, really? Oh. Oh, okay, yeah, the formula for, I'm sorry, I just turned it around in my mind, but yes. So g of x is 1 over 1 plus x squared. So I put g of x in the place of x for the formula for f, so 3 times g plus 1, which is this. Okay, good. Yeah. Yes. And of course, you could simplify that if you wanted to, right? Like you could make a common denominator of x squared plus 1 if you're so inclined. But anyway, any questions about number 1? Okay, some of you got it, right? Yes. All right, good.
I got that right. Let's go.
You got that one? Yes. So, woohoo. Right. So even though I have not covered this kind of problem before today, I think that even if I didn't, most of you probably could have solved this problem day 1 in here, right? Honestly, your previous math work should have got you to this point already, right? I mean, but the letters can be intimidating, right? So, yeah.
I have a question.
Sure.
If you multiply by 2m to get to the other side, and then you divide, would it be by m and k, or is it just 2k?
If I multiply both sides by 2m, right?
Yeah.
I have 2mk is 2m times p squared over 2m, right?
Yeah.
These 2m's cancel, so I get p squared here. Then, to solve for m, I divide by 2k.
Oh, 2k. Okay. Okay, that makes sense.
Yeah.
All right.
Now, problem 3, it might have stumped you, right? Who got stuck on number 3? Like some people, right? That's okay. So, that's okay. But let's understand that you can do it. Like if you look at it, think about how it was done. You can do it. You can do it. So f of x times g of x. So how does that work? Well, if I plug 2 into it, we get f of 2 times g of 2. But what is g of 2? Well, that was given to us to be 5. So 2 times 5 is 10. F of 10, what is f of 10? Well, f of 10 was given to you to be 7. So the answer is 7. So yeah, the answer is 7. Yep. Yep.
Can you go back to the problem, please? So what if you like multiplied both sides by p2, and then you've got
P2.
yeah. It's p2 divided by 2m.
Oh, okay. P2 divided by 2m. Go on, yes.
So if you multiply both sides, sorry, p2 like p squared. Anyway, if you multiply both sides by p squared, and then you got p squared times k equals 2m, and then you can divide both sides by 2.
Whoa. Why are you multiplying both sides by p squared?
Because that's how you can undo a division problem.
But it's not division by p squared. But p squared's not in the denominator. So like, if I multiply the equation that's given by p squared, I'd get, p squared k times p to the fourth. What's that?
I was 7.
Wait, who said what?
I didn't say it.
Who's the culprit?
It's not really the answer. You're not looking at me like you're at your answer.
I don't know who said what. I was looking at the board. Yeah. So what was
P squared divided by 2m, right?
in my defense, I have my glasses not on right now. I can't really see any of you. But what's that?
It's weak knowledge.
P squared what?
Isn't it p squared divided by 2m?
That's what's given. Yes, p squared divided by 2m.
And so if you wanted to undo a division problem,
Yeah.
you could multiply it.
Yes, but we'd multiply by the denominator. Fair enough, sure. So that's what we were doing here. So 2m times both sides.
Yeah, okay, I see what
But that, honestly, I just thought about like, generically speaking, if I have a over b is equal to c over d, just one of the things I know is that that's the same as d over b is equal to c over a. There's this is a rule of algebra. I can trade numerator for denominator on the other side like that. That's a rule of algebra I use. But the derivation of it, of course, is like multiply both sides by the denominator and then solve like I did in the purple over there. But yeah. Why is it so hot in here? It's nice. We should go outside. Yeah, we'll go outside and work on the boards out there. One small problem with that, right? Although there was a professor I was working before this for a couple of years, University of West Alabama. My boss there, also a police officer for West Alabama. I'll tell you what, that's a weird experience. You go to meet your boss. It hasn't dawned on you yet. He's also a police officer, and you're sitting and talking with the dean, and there's this police officer in the room, and I don't know who he is. And then all of a sudden it dawns on me, oh, wait a minute, he's also the chair of math. Chair of math is simultaneously working for the police department of the university. It's like, whoa. Huh. So anyway, he had a board put up outside in Alabama. I just don't know. Like, there's like only 1 month of the year without like a high density of mosquitoes. Maybe 1 month. Maybe February there's no mosquitoes. Every other month there's mosquitoes just in hordes. Right now it's tornado season. Woohoo. But anyway. So f of 2 and g of 2 is given to be 5 and 10 respectively. F times g, we just multiply. Notice the difference. This is not composition, this is multiplication. So we just multiply. F plus g, we add. G divided by f, we divide, right? I was careful not to put f over g because I know you guys don't like fractions, so you're welcome, right? I hope everybody got problem 4. Yep. Disregard the 2. Disregard the 2 and what does this mean? This means we take the function f plus g and we evaluated it too. By definition, the f plus g function is defined by f of 2 plus g of 2. So like, are you asking what happens to these 2's? Or this means we're feeding, this notation means you guys have got to stop talking when I'm talking. It is not helping me, or the person who asked the question. So f of 2, what that means is we're plugging 2 into the function. So it's not multiplication by 2, it's evaluation of the function at 2. That's what happens to it. Yeah. But anyway, I mean, that is the fundamental ambiguity we have to deal with. When you have x times something, or do you have x, you know, like is it 2 times something, or is it 2 getting fed into the function? Because it depends on the context what's meant, you know. Like this, for example, if I write 3 f of 2, it's somewhat clear, and I could put parentheses around the 3 just the same. The 2 gets fed into the f. That's our notation, right? So this would be 3 times whatever f of 2 was. If it's this f, it's 3 times 5, you know? So this would be equal to 15, for example. Let's see here. Turn the page. Here's the first long division problem. So there it is. I mean, step by step, x to the 4th plus 11x cubed plus 18x squared plus 18x plus 20. That is what we get from dividing by x minus 1 for these reasons. And so that means that I have x minus 1 times this. Now, you notice I just said partly factor because I don't want to beg the question, can you factor this quartic, right? Can you guys factor the quartic? I don't know, probably not. I mean, I could try plugging things. If I could figure out a number to plug in here, which makes it 0, then that would tell me that's a factor. But I don't know, I don't think that's going to work. How about minus 1? 1 minus 11 plus 18? Minus 8? Minus 18, no. 10. Minus 1 doesn't work. I don't know. I just made this up, so I don't think it's gonna work out. All right, but so anyway, that's all I could reasonably ask you for that one, just to partly factor it. This one here, I was trying to help you guys out with the complex factor theorem to try to help you learn it today, with all these things I wrote on the board before the quiz, right? This one we have f minus 3 plus I, so that means we do x plus 3 plus 1. x3 plus squared, x plus 3 squared plus 1, which means we should be looking for an x squared plus 6x plus 10 factor. And x squared plus 6x plus 10, it does factor into this with the remainder 0, as you can see here. So I do x squared plus 3x plus 2. These are the details. And so that factors out x squared plus 3x plus 2 times this prime factor. And then you guys know how to factor that, right? This is x plus 1 times x plus 2. So if you got this problem, that's a very good thing. That means you're pretty much ready for my test. If you didn't get this problem, well, try to study it. You know, see if you can figure out what it is you're missing. Listen, I understand. There's a certain amount of people that this is hard, right? Doing this correctly on a test is difficult. There's a lot of steps, right? So you just try to do your best. I do give partial credit for like failed attempts, you know, but you just try. So.
Would you get credit if you like did something like treated beta and this like when you got the original equation that you were dividing by, if you treated it as 0 and then did the whole question with x squared plus 6x plus 9, even if you got to the wrong answer?
Well, I mean, there'd be partial credit for that, but I hope you didn't get 0. No, right. The reason you didn't get 0, of course, is because x squared plus 6x plus 9 is not a factor of this f of x, right? So there are things you can do with what you did. Like there's a meaning to that calculation that could be exploited, but let me move on here because we still have other things to cover today. So I'm gonna put this away if that's okay, guys. That's good? Yeah. Oh, wait a minute, lest I forget. I know you guys are missing like a day without top hat, you know? You're like, I gots to have my top hat. There you go. I have. My other class told me that it could be improved if it was a fedora, but I'm not sure. I'm not sure what I think about that. I think it could be improved if it was just a sheet like this that we pass around every day and like divorce ourselves from unnecessary technology. That would be my preference. It's the 23rd, isn't it?
Yeah.
There you go. My apologies to the people who left early and are watching this video later, I hope. Can I close this? Is everyone top-hatted who wanted the top hat top-hatted? All right, well, I'll leave the top hat open, but I'm going to put away the screen. All right, so let's talk about how to graph polynomials. So how can you guys tell me, how should I graph a polynomial? What do you think? You say factor it? That is, in a nutshell, the center of it, all right? You want to factor the polynomial. That is the key for success, is if we factor the polynomial, then we can see what I would call the critical numbers of the polynomial, in the sense of the critical numbers are the x-intercepts, the places where the polynomial could be 0. And once you know that, then you can figure out where the polynomial crosses the x-axis, and if you draw a sign chart for it, then you can graph it completely. So the homework that I recommended from section 3.4 is basically, it says graph each polynomial function, factor it if it's not already factored, all right? So I think that the book has good advice to you in the homework from section 3.4, right? So let's try them out. See if we can do it. And I also should talk to you about what's called the intermediate value theorem. Maybe I should just say that at the start of it to get it out of the way. What's the intermediate value theorem say? Here's what the intermediate value theorem says. It says if f of a is less than n is less than f of b, then there exists, c between, and we're assuming here a is less than b, okay? Then there exists c between a and b such that f of c is equal to n. This is the intermediate value theorem. Now, this is not always true. This is true for what are called continuous functions. All right? This is true provided that you have a continuous function. Now, what are examples of continuous functions? You say hyperbola? Parabola? Yeah. Well, the most important, for us, the critical thing to think about is polynomials. Every polynomial is a continuous function. All right? So this applies to all polynomials. Where this is most interesting is if we have f of a is like less than 0 and f of b is greater than 0. Right? Then what does that mean? That means that there is a c for some number between a and b. There's a c which is 0. It also works the other way. So like the intermediate value theorem works like this as well. If you have f of a is positive and f of b is negative, that also tells you that there's some c in between which is equal to 0. Here, let me just draw some pictures for you. So for example, if I know that f of 1 is equal to minus 3, right? And I know that f of 5 is equal to 3. And I'm talking about a polynomial. What can you tell me about the graph between 1 and 5? What does it have to do? If it's a continuous function, if you think about this, what that means, if we had a proper definition of continuity, is that the graph you have to be able to draw the graph without lifting the marker. So it could be like this, right? And then I don't know what happens past that. Who knows? Whatever, right? But the point is, somewhere in between, it has to hit the intermediate value of 0. Does that make sense? I mean, that's the intermediate value theorem. Now, does it have to hit just 1 0? No, the graph could wiggle up and down. It could hit 30 zeros between 1 and 5. I don't know without more information what exactly happens, but this much I know. If we're talking about a continuous function, it has to hit at least one place with a 0. Example 2, if you had a function where you're given that f of minus 4 is equal to 2 and f of 0 is equal to minus 1, let's say, what does that tell me? That tells me if we're talking about the graph of a polynomial, I don't know exactly what it does. It could look like this, perhaps. But the point is, whatever it does, it's continuous. There has to be some place between minus 4 and 0 where you have an x-intercept. So let's put the pieces together. Then think about this. If we know where all of the zeros are of the polynomial, then we can graph it, right? Because we know that it can only cross the x-axis where there are zeros. Basically, the intermediate value theorem is what we're using to piece the pieces together. So let's look at a problem in the book here. Does the intermediate value theorem tell you what C is equal to? No, it doesn't. It's what's called an existence theorem, which is, it's only of marginal usefulness. All right, so here we go. Number 29. I may regret this one. Whew, I don't know about this, actually, guys. I may need your help on this one. X cubed. You're like, we're all tired out from the quiz. You're on your own. I hope that's not true. That'd be sad. I'm kind of tired. Plus 2x minus 8. I went to bed last night with my wife talking to my 9-year-old, trying to figure out why he was grumpy. I fell asleep waiting for her to find the source of the grumpiness. I wake up in the morning, I go, what was it? What happened? Why was he upset? And she's like, he'd forgotten. He was upset, but he'd been upset for so long that he'd forgotten why he was upset. How many of us live life like this, Not a good way to be. So she's trying to free him of this in his youth. It's good. Can you factor that? Eek.
Yeah. Like the x cubed, and then the 5x squared, and then the 2x minus 8.
How does that work?
I don't know. It's like a factor itself.
Yeah, I don't know how to implement what you're saying.
No,
I want to believe.
Saying the x cubed and then
The five-
you take them in the groups.
like
But-
The first two terms and then
the first two terms, then the last two terms.
Oh, I mean, you're saying factor an x squared out?
Yeah.
And that's an x plus 5
And then
2.
x minus 4.
I mean, it's a nice idea, but unfortunately,
Doesn't work with that.
yeah, they're not matching up, are they? All right, this one's kind of unfriendly, but it is a homework problem, right? let's try plugging in 1. Does that work? F of 1 is 1 plus 5 plus 2, which is what?
8.
Minus 8?
0.
Ah, so apparently f of 1 is 0.
No, no.
See,
So what would plug is like,
so what does that tell me? That tells me that x minus 1 is a factor, right? So you can either factor it out or you could use long division to figure it out. I'll use long division. X cubed plus 5x squared plus 2x minus 8. And I can factor out an x minus 1. Oh man. Cubed. All right. So that gives me 6x squared plus 2x minus 8. So plus 6x apparently. 6x squared minus 6x. Subtract. 8x minus 8, apparently plus 8. 8x minus 8, subtract 0. All right, so apparently f of x can be factored, and it's x minus 1 times x squared plus 6x plus 8. Can you guys... There is something called the rational roots theorem that could be helpful to us. I don't know if it's in this section or not. Huh, nope. Nope. Descartes' rule of signs in the previous section. Fundamental theorem of algebra. Rational... Yeah, so this is something I should probably tell you guys about. It can be helpful. The rational zeros theorem. Well, I'm not sure that really helps us.
We can completely factor that, right?
Oh yeah, we can.
To x plus 2 is
Yeah, x minus 1 times x plus 2 times x plus 4, right? So what I wanted to mention to you guys is, like, if you want to make the best guesses to try to factor, there's a method to the madness, and the rational zeros theorem on page 348. 348 of your text. It's usually called the rational roots theorem, but they call it rational zeros theorem. And it's got a lot of words. I'll try to translate it for you. It says this: if P over Q is rational number, written in terms of lowest terms, reduced, all right? So like not like 3/6, like 1/2, okay? And if f of P over Q is equal to 0, where f is polynomial with integer coefficients, then P is a factor of the constant term and Q is a factor of the leading coefficient. All right, so in practical terms, what does this theorem tell us? So, all right, this tells us what the possible rational zeros are for a given polynomial if the coefficients are nice. Every polynomial we look at in here has integer coefficients. Integer coefficients just means that the numbers multiplying the powers of x are like plus or minus whole numbers. That's pretty much all of our examples, all right? almost without exception. So in this one, what's the constant term? For our example here, the constant term is minus 8, right? What's the leading coefficient? It's 1. So what does the rational roots theorem translate into for our example? It says if there are rational zeros, they should be what? What is a factor of 1? What are the factors of 1? Plus or minus 1, right? Just plus or minus 1. So in other words, this translates into the zeros that you're looking for are factors of the constant term. So the likely zeros of this by the rational roots theorem should try plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. Those are your natural candidates. For for zeros of the function. I'm not saying that the zeros always have to be given to you, because not every polynomial has rational roots, right? Like, for example, what was this? Example 1, 2, this is 3. We're not done with example 3 yet, but just hang with me here for a second. Example 4, we could look at f of x equals to x to the 5th. Well, not x to the 5th, nothing. X squared minus 2, right? Does that have any rational zeros? Can you factor it? Well, you can factor it, right? F of x is what? X plus root 2 times x minus the square root of 2. So x equals to plus or minus square root of 2 are zeros of the function, which is to say they're roots of the function. And I'm not going to prove it for you, but in fact the square root of 2 is not a rational number. All right, like square root of 2, you cannot write square root of 2 as the fraction of two whole numbers. It's not possible. If you want like a simple explanation, rational numbers, if you punch them into your calculator, they have an eventually repeating decimal. If you look at the decimal expansion of the square root of 2, it never repeats. It just keeps going on differently as you go on. Okay. But this one, check it out. What were the zeros? We had f of 1 is 0. F of minus 2 is 0. F of minus 4 is 0. So, in fact, this cubic is actually very friendly. All of its zeros were rational numbers. So this rational roots theorem is sometimes useful because it gives you a nice short list of things to try. And because textbook problems are written to be friendly and not to, like, kill the students, like oftentimes the rational roots theorem will tell you half of the answers. Okay, and you notice if we had also, we could have avoided the long division too, right? If we had just noticed that f of minus 2 was 0 and f of minus 4 was 0. Yeah. Okay, anyway, so what was left to do? We were supposed to graph it. How do we graph this? So I'll make a number line down here. Here's my number line for f of x. Where are the zeros? There's a 0 at minus 4. There's a 0 at minus 2. And there's a 0 over here at 1. And how does it go? Positive or negative? What's going on? Yeah, we're positive for x large enough. If we put x like x equal to 5 in this, we're definitely plus, right? So plus is over here. What's f of 0? F of 0 is minus 8, right? So it's negative here. These are all linear factors, so the sign flips each time. So we go plus, minus, so then we go pluses up in here, and then minuses over here. So to graph it, all I have to do is to notice my x-intercepts at -4, at -2, and also at 1. And I just follow the signs, right? Follow the signs. So we're going negative. Then what has to happen? We're turning around, right? So that's called a turning point right there. And then we're going to go negative. And then we go back up here again and go on. And of course, my graph is not the scale by any means. This point right here is -8, right? Whereas this one was 1, and this is -2, and this is -4. But there you go. That's a graph of y equals f of x. The hard part is not the graphing, right? The hard part is the factoring, I think. Right? But what do you guys think? Let's look at another one.
So is your y
One more for today. What's up? Yeah?
negative 8 on that going to be your constant?
Yeah. The -8 is the y-intercept. So here's another one. This one is nice. Number 35 will give us our example 5 for today. So here we have f of x equals to 3x minus 1 times x plus 2 squared. So when you have a factor squared or cubed or something, it's said to have a multiplicity. So this has multiplicity 2. But if you look at this, my critical numbers are -2. And how can I make 3x minus 1 be 0? 1/3. 1/3. And so, lovely, now I can, golly, what's wrong with me? -2 and 1/3. Those are my critical, those are my zeros, my x-intercepts for this polynomial. And I'll make the a sign chart down here just to keep myself, honest. So I've got -2 and 1/3. And this one is interesting. What's its y-intercept?
0.
Oof. Well, yeah, actually, honestly, I don't know right offhand. What is its y-intercept? F of 0, right? Plug in 0 to find out the y-intercept. What do we get? 3, 3 times 0, right? That's gone. So -1 times 2 squared, right? So the y-intercept actually is -4. So, I'll draw it down here. The point is, we just figured out that it's negative in there, because that's where the 0 is. If you plug in, let's say, plug 1 into this, what happens? You get 3 minus 1, which is 2. 2 times 9. It's positive over here. What happens at the -2? So here's an interesting one. Because you've got x plus 2 squared, it stays, exactly, it stays the same. So we've got minuses over here like that. So the way I describe it is this. When you have a 0, all right, and it's a square or a quarter or any even power, the graph bounces. So the graph is bouncing like this. It bounces off the x-axis when you got like that kind of thing. So it just bounces there, and then it's got to go through this, -4 for my y-intercept, and then it somehow got to turn around and go through there and like that. So there you go. That's what you're looking at. Y equals f of x is right there. Anyway, we'll do more of these next time, but and we'll also start graphing rational functions next time. So I'm going to turn off my camera before I forget.
Okay, yeah, I can do that.